Well, we all know that we need metals like iron, zinc, copper, and so on to build all the things we need. But you've probably also heard about something called rare earth elements. But what are these rare earth elements? What do we need them for? And what's so rare about them in the first place? Well, let's find out.
Rare earth elements, or rare earth metals, are a group of soft metals mostly belonging to the so-called lanthanoid series. Most of them are actually not rare at all. If we consider the concentration of elements in the Earth's crust, most rare earth elements occur in similar concentrations as the more familiar metals like copper, cobalt and nickel. Gold and platinum, for instance, are much rarer. So why are they called rare earths then? These elements have particular chemical properties that makes it quite difficult for them to concentrate into one place in the Earth's crust. And to make a mineable ore deposit, you need to concentrate an element typically by hundreds or even thousands of times compared to the average crustal abundance. Most other metals such as copper, cobalt and gold have properties that makes it relatively easy for these metals to react with other compounds and form ore deposits via various geological processes. But not so for rare earths, which require very special conditions to form ore deposits, and we'll look at these a bit more closely later in this video. But even where these elements do form an ore deposit, their concentration is fairly low, meaning you have to process a very large volume of ore. What's more, the chemical bonds that rare earths form with other compounds are very strong, much stronger than for most other ore minerals. This means that rare earth minerals are chemically very stable, so you have to put a lot of energy into the processing to break those bonds, typically using very strong acids and very high temperatures. So rare earths are not called rare because they are scarce. The term is actually reflecting the difficulty for these elements to form mineable ore deposits and for us humans to extract the metals.
So what do we need these rare earths for then? Let's have a closer look.
The general term rare earth elements covers 15 to 17 elements depending on the exact definition of the term. Most of these you won't hear about very often, but they all have some really important uses in the modern world, and the applications of rare earths is continuously expanding as researchers find new uses for them. Rare earth elements are sometimes called high-tech metals, and for a good reason. Rare earths are all around us, in phone touch screens, flat screen TVs and other electronics, metal alloys, LED lights, optical fibers, lasers, self-cleaning ovens, and so on. Cerium, neodymium and lanthanum are the most used rare earth elements globally. Most rare earths are used as catalysts in the chemical industry and in the production of high-performance magnets. Particularly neodymium, praseodymium, terbium and dysprosium are used in super-strong magnets, which are a vital component in electronics, including smartphones and electric car engines. Then there are various types of lasers, where rare earth ions absorb energy and then re-emit that energy as light. Other important applications are, for example, fiber optics, which are used in things like telecommunications.
So rare earth elements are very important for all kinds of modern technology, so they're really, really important for our modern way of life. But an increasingly important application for rare earth elements is that stuff over there.
Wind turbines convert the kinetic energy provided by the wind to electrical energy. This conversion happens in the generator, which is hosted in the nacelle of the turbine, and that generator needs powerful permanent magnets. And that's where the rare earth elements come in. Neodymium and praseodymium, for example, strengthen the metals used in the magnets, and dysprosium and terbium make them resistant to demagnetization. So these rare earths are essential for building wind turbines that can produce energy for longer and more efficiently.
So rare earths play an important role in the energy transition, not only in terms of the permanent magnets for the wind turbines, but also things like electric vehicles.
The engines within electric vehicles also need permanent magnets, similar to those used in wind turbines. In addition, some rare earths are already used in certain types of batteries, but research is also going on into whether rare earth elements such as yttrium could enhance the performance of lithium-ion batteries that are used in electric vehicles and many other everyday electronics. The demand for most rare earth elements is growing, and much of this is driven by the energy transition, so building wind turbines and electric vehicles.
Well, let's now have a look at where in the geological environment rare earth elements occur.
Compared with most other metals, rare earth elements don't easily react with compounds that would allow them to get enriched into ore deposits. Rare earth element ions are essentially larger than many other ions, and they also have high field strength, which basically means that they have strong electromagnetic fields. These properties make rare earth elements incompatible, which means it is difficult for rare earths to get incorporated into most common rock-forming minerals like feldspars or mica. Rare earth elements don't react with sulfur either, so unlike most other metals like copper and cobalt, they won't get enriched as sulfides.
But there are some minerals that are capable of incorporating significant amounts of rare earths. The trouble is, these minerals don't usually make up a very large portion of any given volume of rock or sediment, but there are exceptions.
There are minerals that can incorporate rare earth elements in small amounts, and some of these are fairly common, but it is rare for them to contain significant amounts of rare earths, or for these minerals to occur in large enough quantities to make a mineable ore deposit. But sometimes, in very specific conditions, rare earth elements and minerals containing them do get concentrated in sufficient quantities to make an ore deposit. These rare earth ore deposits can be broadly divided into three categories: sedimentary, magmatic, and weathering products. Let's look at the sedimentary deposits first. The most important of these are the so-called placer deposits, also called alluvial deposits. These form when the flow of water sorts the sediments depending on the differences in the density of the different minerals. The minerals are initially eroded from a source rock, so in river systems, for example, the rivers transport the minerals gradually downstream from the source upstream. When the water reaches a slower portion of the river, the heavier minerals accumulate in areas where the velocity of the water flow drops significantly. This is because a slower velocity of water can't keep moving the heavier particles, even when the river is flooding. So, for example, in meandering rivers, the inside bends where the water flow is slower are ideal for depositing the heavier particle, as the water loses its capability to transport the heavier material. You can see this process in action in any river, so the boulders and the gravel, which are heavy, tend to accumulate as gravel bars on the inside bends of rivers, whilst the outside bend of the river is eroded and steep, as all material gets carried away. Some minerals that can contain a lot of rare earth elements can be accumulated in this way because they are relatively dense and resist weathering in surface conditions. The most important of these is the mineral called monazite, which can contain economic amounts of, for example, cerium, lanthanum and neodymium. Also xenotime, which contains things like yttrium, dysprosium or terbium, can form mineable placer deposits. Monazite and xenotime sands are currently mined, for example, in India and Australia, although in most cases placer deposits are mined for other commodities such as tin or phosphates, and the rare earths are a byproduct.
And apart from these rather special types of sediments, there are also some rare types of magmas that can also contain significant amounts of rare earths.
Magmas, which of course are volumes of molten rock, can form at various depths within the earth. The magmatic rocks that can be rich in rare earth elements are usually either so-called alkaline rocks, such as cyanides or certain types of granites and pegmatites, or carbonatite magmas. Carbonatite magmas are themselves quite special as they contain at least 50% of carbonate minerals, which is very rare for magmatic rocks. Carbonatite and alkaline magmas are closely related and they often occur together. They both originate from great depths within the earth, the mantle. Very early in the Earth's history, the rare earth elements were incorporated preferentially into the mantle rocks. When the mantle rocks undergo partial melting, such as happens in areas where the continents are rifting, the incompatible elements, such as the rare earths, are among the first to go into the melt. Particularly the so-called light rare earth elements, such as cerium and neodymium, go easily into these partial melts because they form larger ions than the so-called heavy rare earths. The melt then rises through the crust and typically undergoes a process called fractional crystallization as it cools down. This helps to further enrich the rare earth elements. In this process, the crystals that form first do not easily incorporate the incompatible elements such as the rare earths, particularly those lighter rare earths that have larger ions. Instead, these get enriched in the remaining magma. Rare earth-rich minerals can then crystallize from this remaining magma, or the remaining magma can be transported elsewhere to form new, rare earth-rich intrusions. Magmatic rocks are at the moment the main source of rare earth elements globally, particularly the carbonatite rocks and rocks around these intrusions that have been intruded by the rare earth-rich magmatic fluids. Rare earth carbonatite ores contain very special rare earth minerals such as bastonite, parasite, and synchesite, all of which are typically enriched in light rare earths like cerium and neodymium. But even more common minerals that are found in these rocks, such as apatite or monazite, can contain a lot of rare earths. For example, the Bayan Obo mine in northern China is hosted in rocks affected by carbonatite magmatic fluids and is presently the largest rare earth element mine on Earth.
Now, the third important deposit type for rare earth elements forms right here at the Earth's surface via the process of weathering. And weathering can be a very efficient way of enriching all kinds of metals into mineable ore deposits.
The deposits that are formed via weathering are called laterite deposits. Laterite is in fact a soil type that forms via deep weathering in tropical and subtropical regions, particularly those with alternate wet and dry periods. When the weathering rocks include rocks that contain rare earth elements, such as carbonatites, the rare earths can be enriched into an ore deposit even if the original rock might not be very rich in valuable metals and elements. Surface waters gradually weather the bedrock, breaking down the minerals that contain the rare earth elements. The rare earths and other compounds then travel downwards and accumulate within specific layers within the soil profile. A good example of this is the Mount Weld mine in Australia, where weathering of a carbonatite rock has resulted in the formation of a laterite zone up to 70 meters thick, enriched in specific rare earth minerals. But laterite soils also contain clay minerals, and clay minerals are often electrically slightly charged. So they can actually attract rare earth ions that have been removed from the original rock, so that the rare earth ions attach themselves onto the surface of the clay minerals. These are so-called ion adsorption clay deposits. They are not usually very high grade, but they are relatively easy to process to extract the rare earth elements compared to rare earth minerals. The majority of the heavier rare earth elements, such as dysprosium and terbium, are actually currently extracted from ion adsorption clay deposits.
So geologically, the sources for rare earth elements are quite diverse, even though in most cases the concentrations are too low to allow for economic extraction. And as the demand for rare earths and indeed all other metals keeps increasing, there are also some geopolitical concerns regarding the global availability of rare earth elements.
At present, China is the largest producer of rare earth elements ores, followed by the USA and Myanmar, whilst production elsewhere is very minor. What's more, the refining of rare earth elements ores and the production of permanent magnets are almost completely controlled by just one country, China. The reliance on a single country means that the global supply chain for rare earth elements is very susceptible for disruption. There have already been some concerns about this, with China having a history of restricting the export of refined rare earth elements and permanent magnets, most recently this year. Other countries are stepping up their efforts to mine rare earth elements, but refining and magnet manufacturing capabilities also need to be significantly enhanced to reduce the impact of potential supply disruptions.
So there are concerns globally about the availability of rare earth elements. And this is not helped by the fact that recycling of rare earths is at present not very efficient.
Commercial recycling rates of rare earths is still extremely low, with less than 1% of rare earths being recycled from waste. This is due to inefficient collection infrastructure for waste containing rare earth elements, low rare earth concentrations in most waste products, and technological difficulties. In electronics and permanent magnets, the rare earths have been blended with other metals, so extracting them out again can be very hard, because you essentially have to process the material as you would process primary ore. But perhaps more critically, a computer's hard disk drive, for example, might contain just a few grams of rare earth elements. So a major hurdle in recycling rare earths is the lack of economic incentive and viability. Researchers are continuously working on new techniques that hopefully make it easier and therefore more viable to refine and recycle rare earth elements. But at present, we still need to produce pretty much all of our rare earths from mining.
So, rare earth elements, not so rare in fact, but nevertheless potentially posing a little bit of a challenge in terms of resourcing our modern way of life and the energy transition. Research into rare earth elements is a relatively new field in earth sciences and indeed in terms of their industry applications. So it's going to be really exciting to see what the future holds for these intriguing earth resources.